Well, hello there. Dr. Scott Stevens back again with another video, this one continuing with discrete probability distributions, but talking about their means and variances. Back in Chapter 3, you learned how to take the mean, find the mean or the variance of any set of data, but you can also do it with random variables, with probability distributions, at least in the discrete case. And that's what today's class is about. Let's take a look. I'm going to go back to my example of West Virginia KENO, the game we talked about last time. But last time we focused on how many of the numbers that you picked were winning numbers, the number of matches that you had. Of course, that's really not the question that would most interest you. If you play West Virginia KENO, because you want to make money, so we care not just about what the probability for the number of matches is, but how much money you get for winning that. For example, if you pick 10 numbers and don't hit one single matching number, you still get $5. But as we can see, that happens a little less than 5% of the time. There's a possibility that you'll make up to $100,000 for your $1 purchase in this game, but the probability of it is staggeringly small. I've taken this table and reduced it a bit to kind of just focus on what the different payoffs are and what the probability is for each. And as you can see, the probability of having 1 to 4 matches added up to about 89%. So the question I want to look at is how smart, or stupid, is it to actually play this game? Well, there are some different ways that you could reason about it. One way you could say is this. The number of matches could be 11 different values, anything from 0 to 10, and I make money for my $1 ticket on 7 of those 11. That's a good deal. A second way to think about it would be the most common thing to happen is that I lose $1. That's a terrible deal. Both of these are decent points so far as they go. Or you could go some further and say there are only 8 different payoffs in terms of the money you can get, and you make money on 7 of them. 7 out of 8, that's almost 88%. That's terrific. Unless you flip it on its head and say, no, 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 no. If you look at the 0 payoff, that happens 89% of the time. You actually lose money 8 times out of 9. This is even a worse idea. Well, it turns out that all of these lines of reasoning catch part of what's going on, but none of them catches enough. It's certainly true that most of the time, in fact, you do lose money. 89% of the time, you're going to lose money. And that can't be ignored. But that doesn't tell the whole story, because when you do win money, sometimes you win a lot more money than that $1 that you risked. So there's two things that both have to be taken into account. How much money will you make, and how likely is it that you do? And that's what we're focusing on here. A more important question is just this. How much do you win on average? There are several ways to think about this, but here's an intuitive way. If you played this game over and over and over by buying tons and tons of lottery tickets and filling in random numbers on each, then on average, how much would one of those tickets bring you in? And that's to depend both on the probability and on the payoffs. Let's see what we can do with that. Here's what you shouldn't do. Take every possible payoff, multiply it by, add all the payoffs together and divide it by 8, the number of different payoffs. This is obviously a really stupid way to work. That would say that on average you make $13,000 from a lottery ticket, and you know that can't be right. What's wrong with the calculation? It treats every one of the outcomes as being equally likely, which they are most certainly not. But the way that you do this correctly is not much more complicated. All you do is this. List all possible values your variable can take on. That's what this is over here. Secondly, multiply each of these values by the corresponding probability. This times this, this times this, this times this. And when you get down to the bottom, simply add up the results. Don't divide by anything, simply add them up. If you do that, you will have found the average value of a lottery ticket. Let's go ahead and do it. I've taken column 1, I've multiplied each thing in column 1 by the corresponding entry in column 2. That's why I call this third column here 1 times 2. So $5 times about 4.5% turns out to be 22.9 cents. 0 times anything is 0. $2 times 0.051 is about 0.103. And we've done that all the way down the column, and when we finished, we simply added the results. The result is the average value of that lottery ticket, and it turns out to be 61.7 cents. Which means you pay $1 for a ticket, and on average, West Virginia gives you back 62 cents. That return on investment is about negative 38%. Sometimes people call lottery tickets a tax on people who can't do arithmetic, and this is why. Obviously, the reason that the state runs the lottery is to make money, and what we can see here is they make a pile of it. It turns out that what we're calling the average payoff can be called that, but more precisely it could be called the mean payoff. And interestingly enough, when we're talking about a random variable, like how much this ticket's worth, the most common term to use is a completely new one, the expected value. Now, I got to be honest with you. I am really sorry that somebody decided to name this the expected value, because that's a terrible name. The expected value is not the value that you expect. We just saw in this game the most common thing to happen, 8 times out of 9, is that your ticket's not worth anything. That's what you'd expect, but the expected value, as we just saw, was about 62 cents. The expected value is on average how much you would make, which you can think of empirically as saying if I did this over and over and over and over and wrote down the results each time and then averaged together all those numbers that I got, well, there'd be a lot of zeros in this case, but every once in a while you'd have a 400 bucks. Heck, every once in a while you'll have a 100,000 bucks. Average them all together. The more that you average together, the closer and closer you will be to the expected value. So if they sell 1,000,000 tickets, then on average I'll make 61.7 cents on each of those 1,000,000 tickets, which means my total money for West Virginia is going to be pretty close to 617,000. It won't be exactly that because of randomness, but it'll be close. All right, not only can we find the mean, the expected value of a table like this, but we can also compute the variance of that variable. And it's pretty close to what we did before. Let's take a look and see part of what's going on here. Here are the values of all the values that our variables took on. And here's the average we just computed. Remember how we did standard deviation and variance before. First step, find the deviations. Take every possible value, subtract off the mean to see how much deviation you've got. Here the payoff is 0. The mean is 61 cents. The difference of those two is negative 61 or 62 cents. And we do that all the way down the column. The second thing that we did back in chapter 3 was to square each of those deviations. And that's what we're doing here. 4.38 times 4.38 is 19.21. Negative 0.62 times negative 0.62 is positive 0.38. And we go all the way down that column. But now we have one more step, because back in chapter 3 we simply added the numbers in that column. Not now, because they're not all equally likely. The one more step is the one that we just used for the mean. Every one of these numbers gets multiplied by the corresponding probability before you add them up. 19.21 gets multiplied by 0.04, 0.38 gets multiplied by 0.88, and so on all the way down the column. When you get all those values, add them up, and the resulting number here, 1,247 and some change, is the variance for this calculation, for this variable. That's a pretty big one, but it's easier to understand the standard deviation. We'll do what we normally do. To get to the standard deviation, we take the square root of the variance. Here's the variance. Taking the square root of that gives $35.33. I'll remind you that on average, you're only making 62 cents per ticket. But the variation, the standard deviation of how much a ticket's worth is huge compared to that. That's because every once in a while you win a fortune, but most of the time you win nothing at all. This distribution is very highly skewed. Okay, that's all you have to do for the calculations, and I won't be asking you to do this kind of calculation very often. When I do, because the math is kind of tedious, either we'll use Excel or I'll give you very simple numbers that work out nicely. You should be able to do this kind of problem, but we won't be doing it very often by hand. However, it will let you know what I mean when I say this distribution has a mean of that much, an expected value of that much, which is the same thing, or it's got a standard deviation or a variance of that much. It's always this calculation that underlay that kind of statement. A lot more that I could say. What you see on the screen here are a few different results that are true about variances and expected values. And some people have said that the difference between excitement and fear is that fear is excitement without the breath. I find these results pretty interesting, and anybody who'd like to know more about them, I'll be happy to talk to you about them. But this is 191, and I'm glad to tell you, you don't need to know this stuff. Okay, that's what we'll do for today. Have a good one.